So this is a phasor diagram that we got, and we know the phase angle between voltage and current is your power factor angle phi. So this is the phasor diagram that we got. So we can also draw a different phasor diagram by taking voltage as a reference, but we have taken current here as reference. So today we are going to study short transmission line. Okay. So the subcontents of short transmission line are modeling. Then we will see ABCD parameters. Then phasor diagram, and then after voltage regulation. So there are three types of transmission line. Short we are studying now. Other one is medium, and the next one is long. Okay. So these are the three types of transmission line. Now, why we study why we study the modeling of transmission line. So the reason what is the reason that we study the modeling of transmission line? So we have to calculate the voltage regulation of the transmission line. Okay. So we have to deal with the voltage fluctuations in a power system. So if we model the transmission lines, we'll know about its parameters like capacitance, reactance, impedances. So we can calculate the voltage at receiving end and sending end. Then after that, we can calculate the voltage regulation, and we can try to define some ways to compensate the voltage drops and all that things with the help of voltage regulation. So we do modeling to calculate the voltage regulation and to define solutions for low voltage and high voltage at receiving ends. Second thing is to calculate the I square R losses. So we have to also see the ohmic losses. Okay. So these are the few reasons that should be kept in mind as why we are studying this transmission line modeling. Okay. So this is the fundamental. Now we will start with the modeling. Okay. Now the first heading is model. Okay. So let's draw the basic circuit of the transmission line or how the model looks like. So this is your sending end voltage. This is your output voltage VO, or we can say it as receiving end voltage VR. This is your resistance. This is your inductance. Okay. So this is the circuit we have to deal with. Now we apply KVL here. Okay. Apply KVL. Okay. So we will get minus Vs plus. Let's suppose the current here is Is. Okay. As you can see, the load current is also IR, but it is also equal to Is. So just keep that in mind, and we will apply the KVL here. Plus minus V plus ISR plus ISG omega L plus VR equal to 0. So we will get Vs equal to VR plus Is R plus J omega L. Okay, so this thing here can be written as Z. Okay, and this is is also equal to IR. As you can see here, is equal to IR. Okay, fine. So let's modify this equation now. V is equal to VR plus IR Z. Okay. Now we all know the basics of ABCD parameters. So okay, so we will try to compare this equation with the ABCD parameters in the next slide. Okay. Now you have got this equation. Just keep that in mind. Okay. Now one thing we should also note here that capacitance in short transmission line is not present. Okay, because the leakage currents are very low. So there in the modeling we have only R and N. Okay, so we have got to know about the modeling. Okay, so we will move on to the ABCD parameters, the second sub topic. Okay. Okay. So now we have to use that equation and compare it with ABCD parameters. First, we should know what are the ABCD parameters and equations. So it is given by V. So this is the standard two equation for the ABCD model. Okay. Okay. Keep this in mind. Now we had the equation Vs equal to Vr plus Zir. Okay. Now compare it with this equation. First one, we get A equal to 1, B equal to 10. Okay. This is the first part. We got A equal to 1, B equal to 0. Now we know Is equal to IR from the previous circuit diagram. So compare this with this equation. So we get C equal to 0 and D equal to 1. Okay. So these are the four parameters we get by equating the obtained equations from the circuit diagram with the ABCD parameter model. Okay. So let me write the ABCD model. Okay, this is the ABCD matrix and putting the values. So this is your ABCD model of the short transmission. Okay, with A equal to 1, B equal to Z, C equal to 0, D equal to 1. You can see one important note that A is equal to D is equal to 1. Okay, and A D minus BC is also equal to 1. Okay, so these are the two properties that we study. This is called symmetrical. This is reciprocal. If A and A are equal, then system is symmetric, line is symmetric. And if this determinant is 1, then the line is reciprocal. So these are the few information we obtained from the ABCD parameter modeling. Okay. Now we should move to the third topic. Here's the diagram. Now we have to first start with the equation that we have. Or so this is what we have. Just open this equation. Now we have to first choose the base, the reference to draw the phasor diagram. Okay. Let's suppose this is the base. Okay. Now, as we can see, if this is a the lagging load or the lagging parameters will be here because there is RL, there is no capacitance involved. So current will be lagging here. Note this point. Okay. Yeah. So we have to choose the base first. So we can choose between current or the voltage. So let's start with, let's suppose we have chosen the base as the receiving end current IR. If the current is lagging, so the voltage will be somewhat here. Okay, this is supposed to be VR because current is lagging. So in anti-clockwise direction, the voltage will be upside. Okay. Now see, we have to add this voltage in this VR, and we know resistance does not give any phase shift. So this voltage term will be in the same phase as this IR. So parallel to IR, we will construct a small line like this. This is your this term R into IR. Okay. Now due to this J, a 90-degree phase shift will be there from the straight line. Okay. So perpendicular to IR, we will be drawing a straight line. Okay. Like this. Okay. Now this is your J omega L IR, and this is finally gives Vs. So join this point, this point. This is your Vs. Okay. Now, let me denote every point. This is your omega L IR. This is your R IR. This is your Vs. Okay, fine. Okay. So this is the phasor diagram that we got, and we know the phase angle between voltage and current is your power factor angle phi. So this is the phasor diagram that we got. So we can also draw a different phasor diagram by taking voltage as a reference, but we have taken current here as reference. Okay. So this is how we are going to see the phasor diagram. Now let's move on to the last topic for today, that is voltage regulation. So what do we understand by voltage regulation? So actually, let's suppose there is a terminal, and there we are getting some voltage V. So we want that at all point of time we will get the same voltage V there. Okay. So we don't want any fluctuations in the voltage because it may hamper whatever the device we are going to connect to that terminal. So we want fixed voltage. No fluctuations. Okay, so this is the desired condition. So voltage regulation gives us the parameter that deals with the fluctuation. So we can see what is the fluctuation in the voltage, how voltage is changing at the terminal. Okay, so mathematically we can say voltage regulation is so voltage regulation is the voltage at no load minus voltage at any load by voltage at any load. This is for the general, this is a general formula, but we are scripting with R. So for the short transmission line receiving in voltage. So if you are to calculate the voltage regulation for the short transmission line, we have to find the voltage at the receiving end for no load, the voltage at the receiving end for any load, and divided by the same voltage at any load. This will give you your voltage regulation. Okay. Now, if we see the equations that we have got earlier, the main equations. Yeah. Now, if we suppose there is no load, so IR will be 0. So Vs equal to VR. Okay, because this term becomes 0. So this VR no load is Vs. So voltage regulation will become Vs minus VR at load by VR at load. Or in general, we can say Vs is AVR plus VIR, but for no load, this term becomes 0. So Vs by A is VR at no load. So in general, this will become Vs by A minus VR by VR. Okay. So this is your equation for voltage regulations at load for this is for general, this is for short transmission. Okay. Now let's summarize all the things that we have studied. First, we got to know the equations for the short transmission line. Vs is VR plus ZIR and Is is IR. We got ABCD model of short transmission line as 110Z. We also got A is equal to D, that is your symmetric, and AD minus BC is equal to 1 reciprocity. Okay. We got voltage regulation for the short transmission line as Vs minus VR by VR for short transmission line. And for VR general, we have got Vs by A minus VR by VR. Okay. These are the things that we have studied, and we have also drawn the phasor diagram and the circuit diagram. So these are the
basic fundamentals of short transmission line.